righty. So you're starting count 2 now, and all the starting lessons are very straightforward. They're just introductory lessons. So all the lessons this week will be very basic. Hopefully it'll go well. That is to say, however, it's foundational, so you better have a strong foundation. Today, we're talking about sequences. What's a sequence?
Sequence is a number of like
Bunch of numbers. Let's call it bunch of numbers following a pattern. Not random numbers. Okay? An example, if I told you the very first sequence you ever learned, 1, 2, 3, 4, 5, that's a sequence. What kind of sequence is it? Arithmetic. You're adding one each time. Or 1, 2, 4, 8, 16. What kind of pattern is that? Geometric. You're multiplying by 2 each time. Lots of different types of sequences. You could alternate. We'll talk more about that in due time. Is a sequence the same as a series? Or if not, what's the distinction? Okay. The sequence is a pattern. A series is the sum of a sequence. It's the sum of that pattern. So in terms of notation, if I told you 1, 2, 3, 4, etc., I could denote two things. I could say, what is a sub 1? And that means what is the first term? And that is 1. I could also say, what is a4? And that is 4. It's the fourth term. I could even say, what is a sub n, which is the nth term. All right. The formula for the nth term is the general term. So, for example, if I said, hey, here's a pattern, 3, 7, 11, 15, and you'd say the nth term is 3 plus 4n. Does that work? Assuming you start with the first term, and it's n minus 1. Start at 3 and add 4 oh so many times. Don't add 4 any for the first term. Yeah? That says. You with me? Okay. That's called the general term. The term generating formula, if you will. Sequence versus function. There's a lot of similarities between sequences and functions. Let's say we compare a sub n, which is 3 plus 4 n minus 1, with f of x, which is 3 plus 4 times x minus 1. There's a lot of similarities to sequences and functions. Both have rules for generating terms. The differences, some of the differences are that, first of all, n is whole numbers only, not real. Actually, not. The domain isn't all real numbers. I shouldn't say not real. It is real, not all reals. You could say there's no such thing as the 3.2th term. There's the third term and the fourth term, and nothing in between. So it's not continuous. Sequences are not continuous. They are what's called discrete. All right? A little bit more vocabulary, just basics of sequences. Bounded. A sequence is bounded above if, think of it as a ceiling. There is some number L so that A sub n, or all terms, are less than or equal to that number. If there is a top floor, a ceiling to the terms, then it is bounded above. A sequence is bounded below if there is some number L so that A sub n, or all terms, are greater than or equal to that bottom floor. Just like you have limits from the right, limits from the left, and the limit, same with bounded. You could have bounded above and bounded below. And if a function is bounded above and below, then it is just bounded. A sequence is bounded if it is bounded above and below. And below. For example, A sub n equal cosine of pi n. Give me the first term of that sequence. First thing that goes in is, assume the first thing that goes in is 1. So the first term is negative 1. The next term is 1. Third term is negative 1. Fourth term is, okay, so it is bounded above and below, bounded below by negative 1 and above by 1. So it is bounded. Monotonic, think one sign. Now, that one sign is really a reference to the derivative as one sign. But monotonic sequences are sequences that always increase or always decrease. They do not go back and forth like the previous one we just talked about. We're always getting bigger, we're always getting smaller. Monotonic. Besides the wrong one. All right, so let's start off with some softies, and these are comically easy. I think you'll find most of them. Given each sequence, I give you the general term, find the first 4 terms, and then graph. So I'll do one together with you. A sub 1. Assuming that n of 1 is the first value in, what do you get when n equals 1 goes in? What's the first term in the sequence? Negative 2. What's A2? 4. What's A3? Negative 6 and A4. 8. When you go to graph that, focus on the right side of the graph. We do not usually go the left side of the graph. That's very rare, if not unheard of. And I'm going to go negative and positive, 6 and the negative. So we don't have anything at the origin. Typically you don't say the 0th term. The first term is negative 2. So this here, the x-axis is the term number, and the y-axis is what the term is. So when I locate that first point, the first term is negative 2. The second term is positive 4. The third term is negative 6. The fourth term is positive 8. Does it look like those terms are approaching a limit or spiraling out of control? Okay, you would say that diverges, then we'll talk about that in a minute. Try the next 3. Give me the first 4 terms, then sketch the sequence, or at least the first 4 terms of the sequence. If you're thinking that's boring, then what are all the terms here? Yes. Okay, you're doing fine. Okay. Nope, we're not ready. We're still ready. Sorry, my bad. Okay, so for the third term, did you get 1/2 or third sequence? 1/2, 2/3, 3/4, and 4/5? Is this bounded? Is it bounded below? Okay, there is not a number that is less than or equal to all terms. I disagree. There are infinite number of numbers that are less than or equal to all terms. 0 is less than or equal to all those terms. Do you agree? 1/2 is less than or equal to all those terms. Do you agree? So try again. Is this bounded below? Yes, it is. Is it bounded above? It is bounded above. Above by what? 1. It is therefore bounded? Yes. Is it monotonic? It is monotonic and bounded. The fourth one, what are the terms? -1, 1/2, and this is probably the second most famous sequence in all of math. It's called the harmonic sequence. The series is more important than sequence, but that's okay. It goes something like -1, 1/2, -1/3, +1/4. Is this bounded below? By what? Above. By what? And is it bounded? Is it monotonic? Does it have a limit? Do the terms approach a limit? What is it? If the terms approach a limit, we need a word for that. What should we call that? Converge. These converge. All of these converge, which is to say the terms approach a limit, a finite numerical limit. If a sequence has a limit to the terms, if there's a finite limit to the terms, then the sequence converges. The sequence diverges if it fails to converge. Notice it doesn't mean it diverges if it goes infinite. That's not necessary. It could bounce back and forth. It could do a lot of things. It doesn't have to be infinite to diverge. Let's go with what a problem will look like for this topic. If the question says, tell if the sequence converges or diverges, show the limit as n goes to infinity of the terms equals a finite number or not. To prove your answer, it is not just yes or no. It's justification work. Okay? So when I say find if the sequence converges, don't give me yup. That's not going to do it. All right, so the limit as n goes to infinity of natural log of n over 3 is what? Okay. I thought maybe you are not going to do on the AP test because it's a very straightforward limit. What is the limit? Infinity. The terms get infinitely large. which is to say the sequence diverges. Terms get bigger and bigger. What about cosine of pi over n? The terms are -1, 1, -1, 1, -1, 1. So you would say the limit doesn't exist. There are many reasons the limit doesn't exist. One is because it gets infinitely large. Another is because the left and right hand limits are different. Another is oscillation. If a function oscillates, then it cannot approach a number. This also diverges by oscillation. Fails to converge. The third one, the top goes to infinity, the bottom goes to infinity. You might ask then, does that mean I need to do L'Hopital? And the answer is no. You may use end behavior here, if you know it. What does the infinite limit approach? 0. So, did we answer the question yet? No. We conclude convergence. There is a finite limit to the terms. The terms approach 0. Therefore, the terms converge to 0. All right. Last but not least, this is actually a pretty big idea, very useful in Calc 2, but we haven't touched on it much. These graphs have very similar growth rates. The question is, which has the more powerful growth rate? Now, this one, you guys have great end behavior skills, but this one might be new, so let's go with L'Hopital because there is some question. The top goes to infinity, the bottom goes to infinity, and so by L'Hopital we can investigate further by comparing 1 over n to 1 over 2 root n. Question, shall I take the limits and say 0 over 0 and therefore get caught in an endless L'Hopital loop? Or instead, is there something else I can do? Yes, rearrange, simplify before saying, oh geez, here I go L'Hopitaling forever. Because you will be going L'Hopitaling forever if you don't simplify. This is 2 root n over n. That's equivalent to 2 over root n. So the infinite limit is 0, and we conclude converges. Which is the more powerful then, the root or the log? The root one. Okay. Next idea. From a pattern, finding the general term. This is fun. There are lots of ideas that should go through your head. In order to generate odd numbers, think 2n plus 1. In order to generate even, think 2n. Alternating negative could be -1 to the, -1 to the n or -1 to the n plus 1, depending on if you wanted to start positive or negative. Sometimes you'll see this, cosine of pi n. That is used sometimes to get a generating alternating negative. -1, +1, -1, +1. This is far more common, but this is once in a while there. I don't want you to be fooled. Arithmetic, think linear. I'm not a big slave to the formula kind of guy, but if you remember the sequence term for arithmetic, it looks like that. Generally, or you can just think your way through it, you know, or just use d is the slope equals the change between numbers. Okay, and start from there. I'm just as fine as you think your way through it instead of just regurgitate some formula, which I despise. Geometric is a1, some starting number, times a common ratio over and over again. It's exponential, and it grows therefore very fast. It could alternate signs, alternating signs possible if r is negative. Okay, and then you'll have some calculus knowledge in here going on. So, in this case, I give you this sequence and I want the general term. The general term or the nth term could be found by what form? 2n plus 1. Always check. If n equals 1, a sub n, a sub 1 is? Oops. Fail. So, try again. It is not 2n plus 1 because that would generate a first term of 3, not 1. It should be 2n minus 1. Check your work. You should never miss these. You can easily check, see if you get it right. Just take the time to check, even if it's mental. What about the second one? Take a second to think about it. I'll count to 10. What shall we do for the general term? 2 times negative 1 to the n, or n minus 1 or n plus 1? Does n work? No, because that would start negative. Does n plus 1 work? Yes. Would n minus 1 work? Yes. Okay, there are many possibilities. Alrighty. What about the next one? What's the pattern? Adding 6. So, the nth term is adding 6 a bunch of times to what? 9 plus 6 times n minus 1 is the theory. Does it check out when n is 1? You get 9 plus no 6's. Does that check? When n is 2, you get 9 plus a 6. That's 15. That checks, yes? Okay. Could you also say it is, some people in the last class, they didn't remember the phone, they just said, you know, it's 6 however many times, and in order for that to work, you would have to start off with 3. Does that work? Yeah, that works. If you distribute, it's exactly the same. That's fine. Okay? So my point is, again, there are lots of possibilities. Do what makes sense to you, and I will do some math to make sure your answer verifies. The next one, what do you think? N plus 1 squared. It is perfect squares, but not starting at 1. So n plus 1 squared, does that check? When n equals 1 goes in, do you get the first term? Yes, it checks. What about the next one? What's the pattern? Multiplying, adding, subtracting, dividing? Multiplying by? Negative 3. If you're multiplying over and over, what kind of pattern is that? It's geometric. So what's the formula you would use? Negative 3 some number of times, yeah? And you'd have to take into account where it started, so. Oops, wait a second here. Did I make a mistake? This would be 5 and 3.
We have negative 2, 6, and negative 18.
Negative 2, 6, and negative 18. My pattern wasn't actually a pattern. Good call. That's probably why I fixed it. All right, take it back then. What's the R? What's the common ratio? It's still negative 3, yeah? Okay, so the nth is multiplying by negative 3 some number of times. That's obviously not it. Fill in the rest. What else do you need in there? You need a negative 2 to start with. And then how many times do you multiply by negative 3? N minus 1 times. When n is 1, you don't multiply by negative 3 at all. You just get a negative 2. When n is 2, you multiply by negative 3 once, and so on. All right. Try this one. Let's see how you're doing. Do you have this problem? 5 fourths, negative 7 eighths, 9 sixths? Okay, do that one. many patterns do you see? No, 3. Actually, I guess you can. Start with the theory, check it out. Trial and error is not a bad thing in these cases. ¿Listos? Give me one of your components. Give me one of your components. Please? What I didn't say, please? Say it again. 2 times 2 to the n minus 1. Is that what you said? I think you're on the right track. Does that work for n equal 1? It doesn't seem like that would give you 4. That seems like that would give you 2. So a little bit changed. 2 times 2 to the n. Okay? What if the person next to you said 4 times 2 to the n minus 1? Does that work? Yes. What if the next person next to them said 2 to the n plus 1? Does that work? Yeah, many possibilities. Okay. So, a lot of possibilities for the denominator. Give me a numerator possibility. What kind of pattern do you see? Adding 2, so that makes it arithmetic. So 2 is the common difference, and we need to figure out how many times do we add it and what do we add to. So talk to me. 5 plus 2 times n minus 1. I believe that will work, and it does. What's the last component I need? The alternating negative. Negative 1 to the n or n plus 1? And if I start to the end, will I start off negative or positive? I will start off negative. That doesn't fail. Negative 1 to the n plus 1 is what it needs to be. Check your work. Check your work. Okay. Last but not least, what is this sequence? It is, I heard somebody say it, it is Fibonacci. It is the most famous sequence in all of mathematics, the Fibonacci sequence. There is no formula for the next term, and that's because it is what's called recursive. The terms depend on knowing the ones before it. Recursive. You must know the terms before to get the next term. There is no general formula. What is the pattern? There is a pattern. What is it? You add the previous 2 numbers to get the next. So 1 and 1 is 2. 1 and 2 is 3. 2 and 3 is 5. 3 and 5 is 8. Now certainly that seems like, okay, that's a nice little thing, but who cares? Well, gosh, this is all, you can take whole classes. It's so cool. I'm just going to give you a little taste, okay? So, Fibonacci, so what? Let's start here. This one is a good starting point. Draw a little 1 by 1 square. And then next to it, draw another little 1 by 1 square. We're going to visualize Fibonacci. Now, the idea is that you're going to add the previous 2 to get the next. So, question is, where should you add? Now, if I add those 2 lengths together, I get a new square that instead of being 1 by 1 is 2 by 2. I'm going to draw that up there. Now, if I add the previous 2 numbers, 2 and 1 is now 3. Draw that off to the left. 2 plus 1 more is 3. Now, draw below. Below is 3 plus 1 and 1, which is 5. Okay. Now draw right. 5 plus 1 plus 2 is 8. Is 8. Okay. Now draw above. 8 plus 2 plus 3, this whole length is 13. And then off here is 13 by 3 and 5, which is 21. Obviously, the addition skills are not awesome. All right. So while all the squares are cool, if you draw diagonals through each box, starting at the inside and working out, then you might say diagonal, 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 diagonal. You get Fibonacci spiral. Now, Fibonacci spirals are pretty amazing because they occur all the time in nature. When do you see a spiral? Snails, yes. Snails, or all those mollusks, they have a Fibonacci spiral to them. Also, trees, acorns. If you look at an acorn from above, all those Fibonacci spiral. Acorn, okay? Also, if you look at a tree from above, when you look at a tree from above, as it grows over time, does it just send branches out, ever just feel like send one this way and that way? It does not. It says it sends the next branch out in a Fibonacci sequence kind of way so as to maximize where it sends each one is a Fibonacci sequence so as to maximize how much sun that new branch gets. If you look at, especially oak trees are pretty awesome, but if you look at the diameters of an oak tree, if you look at the thicknesses of the branches, when it sends a branch off, it'll send one branch off that's minor, and it might have an 8-centimeter diameter, and the major will be bigger, and it'll have a 13. Those two will add to the diameter of the branch before, to the trunk before it. And as you continue to branch, every new tube adds to the length of the one before it, Fibonacci in reverse. Gosh, you could look at the human body. If you look at your hand here, we have all the time in the world here. If you look at this distance here from fingertip to first knuckle, and then add the distance first knuckle to second knuckle, you get the distance from second knuckle to the knuckle at your hand. Those distances add to that distance. Now, if you then add to this distance here, keep going. Add that second distance and the third distance, you get this distance from your knuckle to your palm. Your arm is the same as a Fibonacci sequence. This one to this one, Fibonacci. Your face, this distance to this distance, Fibonacci. At least the perfect face, okay? Maybe not mine. The width also, the distance between your eyes, all of that is a Fibonacci. It actually goes to the idea of Fibonacci plus a little something. Look at the ratio of terms. 1 to 1 is obviously 1. 2 to 1 is 2. 3 to 2 is 1.5. Are you with me? Okay. 8 or 5 to 3 is the next ratio. It's 1.666 and so on. 8 to 5 is 1.6. 13 to 8, you start to see a limit to these terms. They bounce back and forth, but the limit of the terms, the limit of the term to the one before it approaches 1.618, so on. If that number will make anything special to you, that's the golden ratio. Okay? This is the golden ratio.
Well, of course.
It's called phi, and this is actually, some people say phi, I don't say, I say phi. Okay? It is phi, and it is used all the way throughout your features and in life and human beings, but also in art. Da Vinci, you know, the Vesuvius Man, the guy that, this guy. You know that picture? I know that's rude, but I know it's not a great picture, but the idea is all of Da Vinci's work and most artists use the golden ratio, the ratio of your torso to your legs, all this stuff, golden ratio all the way throughout. The Parthenon, 4,000 years ago, golden ratio, this side to that side, phi, golden ratio. Okay, this has been known for thousands of years. This is true. I mean, you do this, somebody in psych do this. If you just give people random rectangles and you just say, hey, which one do you like best? Which one's beautiful? They will choose the one that's the golden ratio. It's amazing. Okay? All right. That said, it is amazing. That's all. I'll stop there. Questions on 103 and 104? Do you still have 103 or did we get through it? Okay, 103 and 104 due today. Hit me.
103.
103, 1 and 2. Did we already do 1? Okay. We did 1, but not 2. Sorry, you'll have to come in for 1 later. 103, 1. What else? Or 2, rather. Excuse me. 103, 2. That's pretty much it. We did a couple. Nah. Okay. Number 2 even. Brandon's the only one to slip around. All right. So number 2, you had a car, if you recall, you had a car going this way. I'll call it, what did you call this? X? Distance west? What do you want to call it? West, okay. I'll call this west, and this is going south, so I'll call it S. Although my S's look like 5s, I'll be careful. Okay, and they want to talk about, at a certain time, what is the distance between the two like? So it's a related rates kind of question. They tell me if W represents the position, then isn't the rate at which position is changing dW dt the speed of that thing? So I'm going to say dW dt is given as 40 miles per hour. And the northbound one, southbound one, ds dt is 50 miles per hour. I'm not sweating science so much here because the distances are growing. West is negative and all that stuff, but in terms of the growth, the distances are growing, so my derivatives are positive. All right. They talk about how this guy actually went through the intersection earlier, 30 minutes earlier than the other guy. They want ddt when the time south was 1 hour and the time of the west is 1.5 hours. Follow me? Okay, what's an equation relating W, S, and D? What's the relationship mathematically? We got trig, we got Pythagorean theorem, we got, what do you want? Okay, so Pythagorean theorem, d squared, you want to do d squared or d is the square root? D squared? Okay, so d squared is W squared plus S squared by Pythagorean theorem. I would normally try and make some kind of substitution, but I didn't come up with anything, and I have quite a bit of information, so I'm just going to keep the 3 variables and take the derivative. 2d dd dt is 2w dw dt plus 2s ds dt, eh? So I'm going to divide out of 2 from each and start some. Do you want to solve then substitute or substitute then solve? Let's substitute, shall we? You know dw dt is 40 and ds dt is 50. So far so good. At the instant they talk about, this guy has been traveling 1 hour. So what is its distance? If it goes 50 miles per hour and it traveled 1 hour, this is 50. This guy going 40 miles per hour, he came through the intersection first, so he's been traveling 1.5 hours. How far does he go? 60. By Pythagorean theorem, this is something like the square root of 3600 plus 2500, or the square root of 6100, or 10 root 61. You with me? Okay, so if I throw those in, 10 root 61, d dt is what I'm looking for. W is 60, S is 50. This should be home free for me. Okay. Any other questions on 103? Yes? No. But I can tell you the problem that we talked about. Did you get 12? How far did you get? Did you get something like $12.68? Oh, that's nice. So I will give you a quick 1-minute rundown. You want to maximize revenue, but the problem is that this is 3 variables. So if you go off to the side and relate a line equation of number to price, then you would get eventually negative 7 over 1.5 P plus 355 over 3, which I changed to negative 14 over 3P plus 355 over 3.
So you're just looking at the black.
If you throw that in there, then you get a revenue equation. If you find R prime positive to negative, you get the price, the best price is $12.68. And that was hard enough, but now the hardest part really comes, and that is, that's not the answer. This is not possible because it corresponds to partial number of trees. So what you should do is go back to this and try to find the best whole number of trees, please. That'll get you maybe started. But otherwise, come in 7th period or after school or give it a go. Okay. Other questions on 103? 104. 2. 5. What? 3. 2, 5, 3. That'll only be 1 day behind. 104, number 2. Number 2 is, okay, did you think you had it, but your answer was exactly half of the correct answer? Or you just didn't even get started? Okay, so the problem was there was a cube that was 5 centimeters on each side, and then it was dipped in brass. Dipped in some kind of coating, so that obviously now the volume is going to change. They want you to estimate how much volume to that coating, which is to say how much does the volume change by. This is the brass layer. We're going to estimate that with differentials. That's dV. And the big idea of calculus that you need to show is dV is V prime at x initial times some side change. Alright, now let's get to the details. The derivative is easy enough. It's 3x squared at the original side 5. What's dx changed by? They say the coating thickness is 0.01. So So what's the x? 0.01, not 0.01. See? What? Now that thickness is extending both sides of the length, right? That thickness approaches both sides. So the x is 0.02. And if you're coming out at half as much, that's why. It's because you only looked at one side changing, it's both sides changing. We should be good then. Okay. 5. Question on 5. Is 5 still a question?
Yes.
Can I get 5 or are you leaving? 5 is the slope field. Did this not go well? This might be something I need to do with you individually. If you don't know how to draw a slope field, I will help you individually. Or watch my lesson again, I guess. Anybody staying and need 2, 5, or 3?
Can you do 3?
3, sure.
It'll be 1 for
3. Okay, so this is called marginal cost. in business calc. Bunchy is not due today, just 1, 3, and 4. Thank you, have a good day. All right, to estimate the true change in cost, that's delta C, we're going to use DC. DC is the derivative at the original point times the amount of change in it. So do the derivative by what? Product rule maybe? Alright. I'm going to go, the cost is here, x equals x. So by product rule, first stays the same. By second stays the same. Follow me? And it says dx, the cost of producing one more, that means the number to produce changes by 1 dx more. Now the derivative we're evaluating at the original, not the new 151, but at the original 150. Oh, no, it said 151 have already been produced. So that's the starting point. My bad. Maybe you made the same mistake I just did. Yeah? Yeah. So that means 151 goes in for x. So I have 151 times 2 times 1 plus 1 squared. And it looks like the change would be what, 302 plus 1, 303. That's digital. You're welcome. Have a good day. Right.
These two aren't due today. The slope field practice and 104.
This one is due.
Oh, okay.
104 is due.
And then, are we ever going to do anything with these?
I will think through. All right. So we'll see. I will ask. I'll try to remember tomorrow. Okay.
Remember, did you just unload it? That's the same for us. I thought it was
We're getting that.
I'm like, it's like don't have it. Yeah, you really don't need it.
Hi. Are you ready?
Yeah.
Oh, ready. 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 I'll start in here and just go outside these questions.
Yeah, that's fine.
You're welcome, Brandon. Have a good day. Thank you.
How do you change it to radians?
Oh, it's not reading? All right. So you'll have 50 minutes plus if you fill up the simulator passing through, you make up time, and it's going to be a lot of information. So, okay, there you go. Good luck. You're welcome. No. Because that's how I felt to make you chemistry. I felt stupid in chemistry. I had no idea what was going on. What?
Hello, Mr. Aikman.
Oh, it was a blast. I had no idea what was happening.
Prerequisite class ever again. That was
We don't have any English.
No, Scarlet Letter.
Excellent.
You work with an anymore.
Oh.
No, I thought you said you worked with like reading. Like, no, that's all we were doing. Water doesn't take like that.
Yes, I am getting set. Go ahead in the hall. I'll be right there. Yes, in the hall, right there. I'll be right there.
Hello there. That's a love song. That's a love song. That's a love song.
Yep. Oh, okay. Thank you. Hi.
So my sister has phosphate.
Are you older than her?
No, I'm a freshman. No.
Okay, thank you. I record the lesson. Will be a little bit late. Thank you. Oh, thank you. Hi. No, All right, hang on just a second, I'm gonna get you a
Hey, Ian, is there anything I grab one?
Just a second.
Oh, pretty good. So good.
Okay.